Hey everyone! Have you ever wondered how big a photon of visible light is? It must be smaller than the pupil in your eye, right? In fact, it should be small enough to fit through a 1 micron slit. Yet, it should also be big enough to completely cover two slits that are spaced more than 1,000 microns apart. So, I guess answering this question is not going to be a trivial thing. Now, in the past, I always used to think of a photon as something really tiny, like a little electromagnetic wave traveling through space at incredible speed. But in the last few years, my views have really changed, and in this video I'll discuss why that is. So if you Google for information about the size of a photon, you will not find one definitive answer. It seems everybody has their own opinion about this subject, or even about how size should be defined. Some say that because a photon is massless, it does by definition not have size, because it does not occupy space like a physical object. But you can also define size as distance or volume over which something interacts with its surroundings, or even with itself. And if that's your definition, then photons definitely have size. Now, in school I was taught that a photon is the smallest amount of energy that can be present in light of a particular wavelength. So photons do have wavelength, and for visible photons that wavelength is generally in the order of half a micron. But wavelength is not the same as size. For humans, size is important, I guess. If you buy a new car, you'd better make sure it's the right size for your family and your garage. And so if you see that the lens can focus light to a spot smaller than a micron, it's tempting to think that a single photon should be smaller than the spot, right? Because light is made out of photons. Well, things may not be that simple. For one, is that spot size really 1 micron? Or is it actually much bigger? One of the most fascinating properties of light is indeed its wavelength. If you look carefully, light constantly reminds us that it must have one. As soon as we create a disturbance in the path of the light, we can observe this phenomenon called interference. And a very famous example where we can observe interference is of course the double slit experiment, where the disturbance in the path of the light is a mask with two narrow slits. So here the light can only go along two well-defined paths, and the result is that we observe these areas of higher and lower intensities behind the slits. And these areas are where the light waves are either in phase or out of phase. Now, this is just one example. We can also create interference by, for example, recombining the light of a source and its mirror reflection. Or we can even manipulate interference very cleverly by using a Fresnel zone plate pattern. Interference is caused by the fact that light is an electromagnetic wave or field. And this is the way you generally see alternating electromagnetic fields visualized, as a wave traveling along a narrow line. Now, looking at this kind of depiction, you should ask yourself a few questions. The picture suggests that the perpendicular magnetic and electric fields indicate the field strength at the direction of propagation, but it also suggests that the field travels along a very narrow line. But this is obviously not correct, if only because magnetic field lines are always closed loops and extend into space quite a bit, actually quite a bit more than is shown in this picture. And since the electric and magnetic fields are always directly related, we know that the same is true for the electric field. So even an electromagnetic field with the lowest possible energy, which we might refer to as a photon, can never be this localized entity traveling along a very narrow line. Instead, it must be something widely distributed in space. On the other hand, if we try to detect light, we find that the detection events themselves are very localized, as well as quantized in energy. We can only detect the field of the light by removing discrete amounts of energy from the field. And when we do this, the process occurs very locally. For example, it can happen when a photon is absorbed in one particular pixel of a CCD sensor. Or should I say in one particular atom in a pixel of a CCD sensor. So this is where things get a bit weird. On the one hand, we know that the field representing the photon is distributed in space, but when we try to detect it, we can only do so very locally. And we might ask ourselves, what do we mean exactly with the term photon? Does it refer to the field or part of the field itself? Or do we refer mostly to the process of transferring energy to and from the field? And now that we're asking ourselves all these questions, how long is the electromagnetic wave of a photon? Is it like one wavelength, or approximately 2.5 like shown here, or maybe a few thousand wavelengths? Now, as I said earlier, my views on what photons are have changed quite a bit in the last few years. In fact, there was this one experiment I did in October 2020 that really got me thinking. I showed this experiment earlier as a side note at the end of a previous video. So what I built was a modified version of the double slit experiment. And the modification I had made was that I had split the path leading to the slits into two spatially separated paths. Each of these paths leads to only one particular slit, and both paths have a different length. In fact, I made the longest path about 40 millimeters longer than the shortest path. And even though 40 millimeters may not sound like much, this distance is equivalent to more than 75,000 wavelengths of the laser light I used. Now, when I brought down the beam power to single photon level, I didn't really know what to expect. But it turned out the experiment still showed very clear interference, even with this additional path difference present. So the experiment suggested that not only can a single photon simultaneously take paths that are spatially separated over a substantial distance, but it also allows these paths to have a very significant difference in length. Now, if you were used to visualize a photon as being a little localized electromagnetic wave, like I used to do, this experiment burns a hole in your brain, because it shows that the interference properties of single photons extend over amazingly long distances in space. And at that point, I realized that my ideas about the photon were completely inadequate. And there were several people that told me the outcome of the experiment had to be wrong. Of course, without offering any particular insights on why. Personally, I'm convinced that the result of the experiment is correct, but I now also think that the explanation I gave for the behavior is flat out wrong. So, we're going to do this experiment again, but now stretch that difference in path length a bit further and see what happens. Will there be interference, no matter how long we make the second path, or will at some point maybe the interference just go away? Let me quickly walk you through the schematic. A helium neon laser produces a beam of coherent monochromatic light, and the intensity of this beam is then attenuated to single photon intensity levels with a series of gray filters. Now, later in this video I'll discuss how that was done. Next, there's a beam splitter that creates the two paths for the light, and the short path leads directly to the detector while passing a second beam splitter. And the other path takes the beam on a little sightseeing tour and eventually brings the light back to recombine with the light from the first path. As you can see, the long path is about 5 times as long as the shortest distance. Now, after the light of the two paths is recombined, it's detected here in a camera where we can look at the interference. Let me show you around the actual setup. Here is the helium neon laser. It's a golden oldie which was produced in December 1979. At its last calibration it was generating less than 1 milliwatt. But wait, does it say in 1985? Now, even though this laser has matured as gracefully as I have in the last 35 years, it's lost quite a lot of its mojo, because now it only produces about 0.3 milliwatts. But all the better actually, because we don't need a lot of light for this experiment. Next in the setup there's a mirror under 45 degrees that is used to control the beam direction, followed by a set of neutral density filters to bring the power of the laser to single photon level. The light then passes through a beam splitter, creating the two paths, and the first path continues in a straight line to the detector while passing a second beam splitter. And the detector, by the way, is a pretty standard IP camera with a Peltier element to reduce thermal noise a bit. The longer path in the setup is routed via a Poro prism to the second beam splitter, where it's recombined with the first beam. And as you can see, there's also a lens here which is used to compact the interference pattern a bit to make the detection more sensitive. The additional mirror for the second path was necessary to achieve a detour of more than a meter long on the base plate. By placing the two recombined beams under a very small angle, the interference pattern displays only a few minima and maxima, which is convenient because a pattern like this allows for very sensitive recognition of interference, even at extremely low intensities. And because the light levels in the room are way too high for doing single photon detection, I also shielded the setup from ambient light. And for this I used a few pieces of cardboard just to give the setup a nice high-tech look and feel. Now the most important question in this experiment is, how can you be sure that the beam power of the laser is in the single photon range? Well, imagine that we have a continuous light beam coming out of a laser and we start adding gray filters that each transmit a certain fraction of the light, say 10%. At some point we will reach an output power in the beam that is equivalent to, on average, only a single photon at any time. So how do we do the calculation? Well, we assume that the light is quantized in discrete amounts of energy. We start out by calculating the maximum lifetime of such a quantum in the setup, given the speed of light and the maximum path length. Now for 1300 millimeters, this value is 4.3 nanoseconds, which means that for an average of one photon in the beam at any time, the photon flux can be as high as 230 million photons per second. And using the photon energy of the laser light, this flux is equivalent to 74 picowatts. With the current output power of the laser, which is 0.3 milliwatts, we can calculate that we need to attenuate the beam by at least a factor of 4 million to get to this 74 picowatts. And this means that we need a filter with an optical density of 6.6 in the beam. Now in practice I was able to detect interference with filters having an optical density of 9. And if we use this last filter setting, we can calculate that the beam intensity is 250 times lower than that of a beam containing on average one photon at any time. So now that we know that we can indeed go into the single photon intensity regime, I can finally show you the result of the experiment. Do we still observe interference with a difference in path of over a meter? Let's not keep you in the dark any longer. This is what we observe in the single photon regime if either one of the paths is closed off. And this is what we observe if both paths are open. Now, there's no doubt about it, even in this case we observe an interference pattern. Hence, at single photon intensity level, the photons do exhibit interference, even if the paths differ by a length of a factor of more than 5, and in absolute length by more than 1.6 million wavelengths. Now, I can assure you, the more you think about this result, the wackier it gets, and I guess wacky results ask for wacky explanations. So, in the previous video on the subject, I proposed a pretty wacky explanation. In an attempt to explain, I suggested that we could assume that the phenomenon of interference is somehow detached from our temporal and spatial observations. So basically my suggestion was, because light travels with the speed of light, it does not experience time and distance, so all paths are covered instantaneously when viewed from the perspective of the photon. But in retrospect, that explanation is rather silly and it raises more questions than it answers. Also, there is a much simpler explanation that actually makes sense. And this explanation was suggested to me by David Nettlinger, a researcher at Oxford University. He very kindly explained where the experiment went wrong. The physics behind it is pretty hefty and it's not like YouTube video material, so I'll try to explain this in my own words. The essence is that the electromagnetic field of the beam after leaving the attenuation filters is a more or less continuous wave or field, like drawn here schematically. And now you're probably thinking, where is the quantization? I thought light was made up of individual photons. Well, yeah, but... The thing is that even though the energy transfer processes to and from the field have a quantized nature, the electromagnetic field itself is actually not quantized. It can basically take on any value. So let me explain this in a little more detail. Contrary to spontaneous emission, which is sort of a random statistical process of energy emission in discrete packages, a continuous laser like a helium neon laser emits a beam of coherent light, and the field exiting the laser is a continuous electromagnetic wave which has a high field strength. And that is because almost all the quanta of the energy are added to the beam in phase due to the stimulated emission process. If such a beam passes the gray filters, it will decrease in intensity because of absorption of a part of the energy in the beam. And yes, this absorption process has a quantized nature and it happens in discrete steps. But it happens in sort of a random manner in time and also spread out in space within the volume of the filter. So each absorption event takes sort of a random little bite out of the remaining field, decreasing the intensity a bit. Now, because the electromagnetic field strength itself is not quantized, this process eventually results in a sort of continuous field strength that is much lower than what we would find in a true single photon event produced by spontaneous emission. The field strength can at times even be almost zero or actually zero. But even though the field is very low, it's still coherent and more or less continuous. So this could very easily explain why we observe interference in this configuration. It's because in essence we have two continuous coherent beams interfering. So yes, the power of the beam is far below single photon intensity level, but nonetheless it's continuous. And this is very counterintuitive if you are taught that light is quantized. So basically I had a poor choice of light source. Had I chosen a fluorescent lamp instead of a laser, my single photon calculation had actually made sense. And of course I would never have observed single photon interference in the current setup. The experiment, by the way, also shows a few other interesting aspects of light. You see that the interference pattern consists of these individual sensor pixels that light up, and it's good to realize that these are in fact not single photon detection events. What we see is CMOS pixels that collected a specific minimum number of photons. And the reason that it is displayed like this is because I cranked up the gain of the camera to a very high level. Anyway, even though we're not observing single photons, we can observe this very interesting phenomenon called shot noise. And basically what we see is that the spatial distribution of photons is not the same for each individual measurement. And this is caused by statistical variations in the photon detection for each measurement. It's also a subtle reminder of the fact that we can never observe interference from just a single photon, because demonstrating interference always involves collecting many photon detection events. In other words, what we do when we look at interference is gathering statistical information about the spatial probability of detecting a photon somewhere. And this probability itself, like the field, is also not quantized. I guess my main problem with understanding the behavior of light was that everybody always told me that the energy in light is quantized. But they forgot to tell me that the electromagnetic wave, so the carrier of the photon energy, is not quantized. An electromagnetic field can be attenuated, diluted by traveling through space. It can be split into arbitrary fractions when passing a beam splitter. The field has no problem whatsoever with this because it's not quantized. But of course, the probability of detection being proportional to the square of the field strength will also be diluted or split. And that is basically what we observe when we look at interference. These dark and bright bands we observe are just the result of local variations in field strength due to phase differences between different paths. Now, if you consider the field as the leading property for the probability of detection, the things we observe in diffraction experiments, like for example the double slit experiment, become almost kind of trivial, because if quantization is not a property of the field, but just of the energy transfer processes between field and matter, the outcome of the experiment is basically what you would expect. But what is definitely not trivial to imagine is how the energy contained in a wave, spread out in space, can be converted back to another form of energy in a very local and quantized event. So to get back to our original question, how big is a photon of visible light? Well, if you consider the photon to be the same thing as the electromagnetic field, photons can be absolutely huge, or at least their volume of interaction can be huge. In fact, within this definition, there is no fundamental limit to its size. But if you define the photon as the quantized interaction between field and matter, then a photon is in fact an extremely localized phenomenon. Now you choose. It's a golden oldie which was produced in December 1979. At its last calibration it was generating less than 1 milliwatt. But wait, does it say in 1985? Huh, I remember that year.